Section 14.7 is about maxes and mins of a function. And just like with functions of one variable, sometimes we'll be talking about local maxes and mins, and sometimes we'll be talking about absolute maxes and mins. Okay. Now, all of the examples in this section in your book involve functions of two variables. And some of the techniques that we're going to use are only valid for functions of two variables. But these definitions and some of the theorems that we're going to encounter apply for functions of n variables, where n could be 2 or 3 or more. Okay. So what I've done is whenever I'm giving you a definition or a theorem that does apply in higher dimensions, my version will be genericized. I'm going to talk about f of p, a function evaluated at a point in n space. The book's going to be more specific and talk about a function of x and y. I'm simply trying to point out which aspects of what we're doing in this section do generalize to higher dimensions, and certainly the definitions of max and min do. Okay, so my version of the definition is just a more general version of the definition that's given in your text, which is for a function of two variables. And so here's what it says. A function of p, so p is just going to be a point in n space, has a local max at a point p naught if two things have to be true. There's an open region containing p naught such that f of p naught is bigger than or equal to f of p for all p in that region. Now, because I'm talking about this being in n space, I'm using the word region. The book in their definition is going to use the word disk because that gives me a nice region in two space. Not that all regions have to be disks, but a disk in two space is certainly a region of two space. If we're in three space, we maybe have an open sphere containing our point. Okay. But that first condition is saying that the point p naught has to be an interior point in the domain. So if the domain has some boundary to it, it can't be on the boundary. The function has to be defined at and near p naught if I move away from p naught in any direction. Okay. And then I need the output of the function there to be bigger than or equal to the output of the function anywhere else in that region. Okay. So if I did have a function of two variables, and here's my p naught, and there's some lovely open disk, if I applied the function to points in that disk, the function evaluated at p naught would be higher than or the same height as the other points in that disk. Okay, so that's our definition, and I just wanted to point out the two technicalities. One is that p naught does have to be an interior point in the domain, meaning that if the domain has a boundary, this does not apply to points that are on that boundary. And the second is just that this is an inclusive inequality, okay? So that if you have a plateau, so that you've got a whole bunch of points all at the same height, that still counts, okay? I also want to just distinguish between p naught and f of p naught. P naught would be the location of the max. Notice it says f of p has a local max at p naught. That's where it occurs. F at p naught is the value of the max. Generally, when I'm asking you to find these things, I will say find the location and the value of the maxes and the mins, and that means I'm asking two questions and I want two separate answers, okay? So one to tell me where it occurs and one to tell me what it is. Okay. All right, of course, this definition is given for a local max, but if I wanted to define a local min, I could very easily do that. I would simply switch the inequality to be a less than or equal to. Okay. And then the next definition isn't given a number in your book, but it's an important definition. So it says f of x has an absolute max at p naught if the function evaluated at p naught is bigger than or equal to f of p for all p in the domain. So that means I don't need to be at an interior point. If my domain has some sort of a boundary, boundary points count. Again, with this definition, p naught is the location, f of p naught is the value, And again, if I wanted to describe an absolute min instead of an absolute max, I would simply reverse the inequality. Okay. So those are our definitions. Okay. We're going to start out by looking for local maxes and mins. Those are also sometimes called relative maxes and mins. And so we want to think about, well, how do we find out where they would occur? So if I think about functions of one variable, if I want to find the relative maxes and mins, I look at critical points. And it's exactly the same thing here. We're going to look at critical points. Okay. So what's a critical point? Well, for a function of one variable, a critical point is a point that's in the domain of the function, but where the derivative is either undefined or doesn't exist. And it's essentially the same thing here. So here's a new definition. F of p has a critical point at p naught if p naught is in the domain of f and either the gradient of f at p naught is the zero vector or the gradient of f at p naught is undefined. That's equivalent to saying it doesn't exist. Okay. So all we're doing is we're replacing the word derivative with gradient. Now I know if a function is differentiable, the derivative is the gradient. But this theorem is going to be true whether the function is differentiable or not. So for functions of one variable, if the function isn't differentiable, the derivative would not exist. For functions of more than one variable, it's possible to have a function that's not differentiable, but the gradient still exists at some point. But if that location is a critical point, the gradient will still be zero. Okay. So, one thing to point out, if the gradient is the zero vector, that of course means that every component of the gradient is zero. So this would mean that all partials would have to be zero. Okay. And if the gradient is undefined, that's going to follow if any one of the partials is undefined. Okay. So maybe you've got a function of three variables, two of the partials are defined, the third one isn't, that's going to give you a critical point. Okay. So this would be if at least one partial is undefined. All right, so let's just practice finding some critical points. We're going to, once we know how to find them, of course, we'll be concerned with classifying them. Are they the locations of a max? Are they the location of a min? Or, as with functions of one variable, are they neither? And with functions of more than one variable, then neither can be more interesting, too. Okay, so we'll have to take a look at that. But let's just say I have f of xy is equal to x cosine of y. Okay. So let's find our critical points. So the gradient of f is just the partial with respect to x, comma, partial with respect to y. That's going to be cosine y, comma, negative x sine y. Okay. So I'm going to first of all just point out that that is always defined. AD is my abbreviation for always defined. I like to write that down because it gives me a visual check to remind myself that I looked for that. Very often, the functions we're working with are going to have gradients that are always defined. And what that means is that it's easy to forget to check, because usually it doesn't make a difference. Okay? But then we encounter the one where the gradient is undefined at some point, and we say, oh, I forgot to check for that. Okay? So I always check for that first, and I write down that it's always defined if that's the case. Okay? So then, for the gradient of f to equal the zero vector, well, that's going to imply that cosine of y is equal to 0 and negative x sine y is equal to 0. So I'm always going to be solving a system of equations. If I had a function of two variables, The gradient is going to consist of two partial derivatives. They both have to be 0. If I had a function of 3 variables, the gradient would have 3 components. All 3 of them would have to be 0. So very important that this is an and right here. Okay, now if cosine of y is equal to 0, that would mean that y is just an odd multiple of pi over 2. I can write that as 2n plus 1 times pi over 2, where n is an integer. Okay. That's going to put me on the unit circle, viewing y as the angle. That's going to put me at a point that's an odd multiple. Whoops, I'm sorry. That's going to put me at a point that's an odd multiple of pi over 2, like so. Okay. Then I also need that negative x sine y is equal to 0. Now, for this to be true, there are 2 options. This is a product of 2 things, so either factor could be 0. So this is x equals 0 or sine of y equals 0. And if sine of y equals 0, y is a multiple of pi. Let's write m pi, where m is an integer. Okay. So I need this to be true and one of these to be true. Okay. Do be very careful as you're labeling things, which ones are ands and which ones are ors. Okay. So I could have that y is one of these guys, an odd multiple of pi over 2, and x is 0. Okay, so that's going to give me some critical points. Let me just write them up here. So x being 0, y being 2n plus 1 times pi over 2, okay, where n is an integer. Okay, those are all critical points. Now my other possibility is that y is one of these and y is one of these. But that's not possible, because if y is an odd multiple of pi over 2, which viewing it as an angle would have me landing here or here, then it can't also be a multiple of pi, which happens to be an even multiple of pi over 2. So this is incompatible with this, so the only possibilities are that I satisfy the second condition by x being 0, so that would be all of my critical points. Notice there are infinitely many of them. That's perfectly acceptable. You can have infinitely many critical points. But we're able to write them all down because we can describe them by just using the integers like so.